Okay, Chuchong, does it look good?
Yeah, I see it. Yeah.
Perfect. We'll get started. Sorry for the delay.
Hi, I'm the Joseph from University of Science and Technology. I'm glad to introduce our recent work on hybrid detection. In this work, we study a new task for multi-person hybrid detection with web for untraceability. Compared with the existing work that focus on single-person scenarios, the proposed task is more realistic and have a broader application value. For example, detecting long-term hybrid behaviors at multi-instance level can be used to analyze attendees' attention level and emotional state change during social interactions or group activities. To support this new research task, we construct a new benchmark and link. We choose to collect data from a diverse set of unconstrained movies to meet the multi-person, unconstrained, and untrained characteristics. Due to the high divergence of the selected movie data source, the capture samples are also more realistic and of great challenges for effectively detecting items. For instance, the pose, illumination condition, and face size also differ a lot even within the same person, same video. Moreover, because of the various type of interaction among instances, there may exist severe occlusion for people in and out scenarios, making it harder for both instance localization and hybrid detection. To perform hybrid detection, previous methods generally take a sequential approach containing face detection, face tracking, landmark detection, and classification of the pre-extracted local eye groups within a rigid temporal window. Such a sequential approach is hard to meet the real-time running requirements under multi-person scenarios, and usually obtains an inferior performance due to unreliable local eye groups under unconstrained cases. In this work, we present InstBlink, a one-stage multi-person eye-blink detection framework that can simultaneously detect human faces, track them on time, and do eye-blink detection at instance level. Specifically, inspired by the recent query-based methods, we use spatial temporal queries to store the face and eye-blink features of each instance within the entire video clip. Applying different paths, shared query features can allow us to achieve face detection, face tracking, and instance level eye-blink detection at the same time. Under this framework, features from some tests can be effectively shaped and interactive to obtain a superior performance with higher running speed. Here we show some prediction results from InstBlink. Our method aware the attendees robustly and detects the objects under given visual appearance and head pose. For more details, please refer to our paper in the project page. Thank you for your time.
Hi everyone, our work is thought. Hi everyone, our work is thought-free adaptive gaze estimation by uncertainty reduction. The authors are Xin Jiabei, Shiguang, and Xilin from Institute of Computing Technology, Chinese Academy of Sciences. The gaze estimator's performance often decreases when they are trained and tested on different domains. The training data are usually collected under controlled conditions, which is convenient to measure and compute the true gaze vector. But the trained estimators are used in diverse and uncontrolled environments. In our work, we aim to improve the gaze estimator's performance on target data. However, due to the privacy and efficiency concerns, it's difficult to access the source data and target data at the same time. As a solution, we first train the model with labeled source data. Then, we adapt the source trained model to the unlabeled target data. The adapted gaze estimator is used to predict the text image. The source-free adaptation is based on our observations about the relationship between domain gap and uncertainty. We discovered a larger domain gap between the target and source leads to a larger model's uncertainty. The uncertainty can be decreased if we enhance the quality of the image and reduce the domain differences. Under the cross-domain protocol, the gaze error increases as the uncertainty grows. Therefore, we propose to reduce gaze error by reducing both sample and model uncertainty. Sample uncertainty is mitigated by enhancing image quality. Model uncertainty is reduced by minimizing the prediction variance. The detailed framework consists of 3 steps. First, we collaboratively train a phase enhancer and gaze estimators on source data. We keep a set of gaze estimators at different iterations during the training. Then, we cannot access the source data. We freeze the phase enhancer and update the gaze estimators in an unsupervised way by minimizing the model uncertainty and maintaining the gaze estimation ability using pseudo labels. Finally, we predict the gaze using the phase enhancer and the mean estimator. We conducted experiments on cross-domain gaze estimation using 4 datasets. 2 of them are used as the source and 2 are targeted. The experiment's results show our method outperforms others on these cross-domain gaze estimation tasks. The visualized examples show that phase enhancement can improve image quality, reduce gaze errors, and model uncertainty. Thanks for your attention.
So good afternoon. Good morning, everyone. So my name is Zhu, and today we will present our work titled Latent-to-Latent Translation for Gaze and Head Redirection. So our target is modifying the gaze directions and head orientations for high resolution full face images without affecting other facial attributes, given the provided directional vectors as the conditions. So our approach involves editing the target facial attributes in the latent space using a conditional gain pipeline. So given the provided target condition CT, we can transform the encoded latent vectors FS into FT hat, and then it can be fed into the generator for image synthesis with edited attributes. So to achieve conditional redirection in the latent space without affecting other facial attributes or identity information, we only project the target facial attribute relating features into a embedding space Z to achieve transformation in an interpretable manner. So we use a with-sharing deprojector to transform the embeddings back to the original latent space for original attribute removal and new attribute addition. So to achieve gaze and head redirection on high resolution full face images, we combine the redirection trans with the gain inversion pipeline, named as redirection transgain. So we utilize E4E as the image encoder and StyleGAN as generator. So during the training of this end-to-end pipeline, we freeze the parameters of the encoder and generator to make sure that the editing is implemented in the original latent space. So given the 18 layers of latent vectors in W+ space, so we introduce layer-wise editing modules for gaze and head redirection. So redirection transgain can adaptively estimate the weights based on arrows between the estimate results and between the inverted results and estimate labels from the latent vectors. So this allows us to determine which layer should contribute more to the desired facial attributes editing. So let's now examine the evaluation results within datasets and cross datasets, comparing redirection trans with state-of-the-art methods. So we evaluated the performance from the gaze and head redirection accuracy, gaze redirection induced arrow to head, and head redirection arrows induced arrow to gaze, and also LPIPs. So here are the qualitative results from redirection transgain, so which successfully achieves gaze and head redirection in high resolution images. So we can observe that the redirection transgain is able to redirect the gaze directions and head orientations while maintaining other facial attributes. So our proposed redirection transgain can also correct the gaze as a compensation for the gain inversion pipeline. It's kind of like a subtask for the gain inversion task by using the same image as both input and target images. So we ensure that the inverted image maintains the original gaze directions, even without explicit gaze direction labels for the input image. So this demonstrates the effectiveness of our proposed method in the gaze correction task. So thank you for listening.
Good morning, everyone. I'm Xiangwei Shi from Delft University of Technology. I'm very happy to be here to present our work GazeNerve 3D aware gaze redirection with neural radiance fields. It is of It's a joint work of TU Delft, ETH Zurich, NVIDIA, and University of Birmingham. First, our work focuses on the gaze redirection task. Given a face image and its corresponding gaze label, the task is to generate synthetic face images with different target gaze labels. Existing methods for gaze redirection tasks can be mainly categorized into image warping and synthesizing new images with deep generative models. However, they both have drawbacks. Image warping method not model large change due to its inability to generate new pixels. While 2D generative models can produce high quality face images and allow for large change of gaze direction, they do not take the 3D nature of this task into consideration. Recently, a nerve-based model of head nerve was proposed to generate face images with efficient control of face attributes. So in our work, we propose gaze nerve. It reformulates this task as 3D neural volume rendering, and it disentangles the face and eye regions, allowing for the rigid transformation. Given the target gaze label and the latent codes related to the facial attributes and the 3D locations as the input, gaze nerve employs a novel two-stream MLP structure to learn the features of eye region showing in yellow and the features of face-only region showing blue. We explicitly apply a 3D rotation matrix on the regions features of two eyes, and then combine the features from two streams to shown in orange to render the whole face. And then we feed 3 features into the same neural rendering module to generate the final 2D images. For the experiment, we show that gaze nerve achieved the best performance on gaze and head pose redirection error, and also the comparable performance on the image quality compared to the state-of-the-art methods. We also visually compared the generated images with the ones by the 2 previous state-of-the-art methods, STAD and head nerve. The blue circled images are generated by the STAD. They show that STAD suffers from the loss of personal identity information. And the red circled images are generated by head nerve, even though head nerve can preserve the personal identity. But they cannot generate fine-grained eyes, and also in some cases, it shifted the gaze direction. Compared to the 2 previous state-of-the-art methods, our work gaze nerve can generate the high-quality face images with target gaze direction and fine-grained eyes. Here are some animations. They are generated by gaze nerve with 3 different settings: changing the gaze label only, changing the head pose only, and changing the gaze and head pose at the same time. Thank you. Please check our paper for details if you are interested.
Hi, I'm Hu Zhenxi. I'm going to present you our research, GFI, the dataset and baseline for this following from 2D to 3D in indoor environments. This following repels inferring where the person in a sense is looking. However, a summary of datasets used for this following tasks reveals defects in the way they collect against point labels. So, we first present 2 key problems. To address the problems mentioned above, we developed a system to record its behavior and released the novel GFIE dataset with reliable annotations. We also proposed the baseline method for improving its following. Some test samples on the GFIE dataset are given for an overview. First, we stated the motivation for this study. We conducted a survey of datasets used for gaze following and found defects in the way they collect gaze point labels. Most datasets are manually annotated, And the subjectivity of annotators may cause annotations to deviate from the actual gaze target. In addition, label intensive is another drawback. The eye tracking device can capture annotations automatically and alter subject's appearance in the dataset. It may bring the gap with the gaze-related behavior in the natural environment. In this work, we proposed a novel system for establishing our GFIE dataset. We use the laser spot emitted by the laser rangefinder to guide and locate the gaze target. After collecting various gaze behavior, accurate annotation can be provided for establishing GFIE datasets. In addition, we introduced a stereo field of view in the proposed baseline method for improving gaze quality. These are our main contributions. Next, we briefly describe the workflow for GFIE dataset generation. The gaze data collection system consists of a laser rangefinder and an RGBD camera, OrthoKinect. OrthoKinect is set to capture RGB and deep images. Laser rangefinder are used to measure distance while emitting laser light. Then we can operate the laser rangefinder to guide the subject's attention target through the laser spot. The subject is always staring at the laser spot while performing in front of the camera. After collecting various gaze data, we needed to build a workflow to generate the GFIE dataset. There are 3 key steps here, including laser spot detection, laser spot elimination, and annotations generation. We first propose the CDBPS algorithm for laser spot detection. Then we use the existing image impacting algorithm to eliminating laser spots. Our GFIE dataset provide annotations, including head bounding box, eye locations, and gaze targets. The first 2 are generated by detectors, where the gaze target can be obtained based on the detected laser spots, camera intrinsics, and mirror distance. Failure case in annotations were manually checked and corrected. These 2 demos are examples of laser spot detection and eliminating laser spots. In the video on the left, the detected laser spots are in the red bounding box. The GFIE is a multi-modal dataset. It consists of over 70,000 frames and contains various gaze behavior of 61 subjects. The dataset split are shown in the table. Statistics from 2D plane to 3D space are also shown in the figure. Some things in the GFIE dataset are displayed here. We also propose the GFIE baseline model. It consists of 3 key components. One module is used to estimate gaze direction. Based on predicted gaze direction, the module that perceives the stereo field of view is proposed to highlight regions that a person pay attention to in space. Then we can infer gaze targets based on the module for generating gaze heat map. A strategy for 3D gaze following is also designed to extend the proposed baseline.
Okay, I'm sorry, but I think I'm going to interrupt the video here because for fairness as well, the other talks were 3 minutes long. Firstly, thank you very much to everyone for presenting for the main papers, that is. Of course, there's CVPR main conference papers, so you will be able to visit them again at the upcoming poster sessions, which I highly recommend that you do. The poster session will begin soon. I recommend that the non-presenters get a cup of coffee and take it easy and head down slowly towards the poster session. It is a long walk, so please take your time. Poster presenters, might be a good idea to hurry up, but please come to the front and then I'll try to help you guys along towards the poster session. Please note that we have to pick up our posters and hang them, so really take your time, the rest of you. And yeah, have lots of coffee in it. See you guys later at the poster session and back here at, I think, 11.